So thank you very much for the invitation. It's a pleasure to be here. So I'm going to talk about more Bernoulli problems. My emphasis is going to be on stationary solutions instead of stable or minimizing ones. And then I will give an application of a theorem we prove about stationary solutions to constructing gravity water waves. And I should say, so everything here is joint work with Georg. Okay, so this is the Bernoulli free boundary problem. Xavi was just talking about it, so you know what it is. For me, well, so it's important to kind of figure out what kind of solutions we want to talk about. And when you're not dealing with minimizers, this is not really obvious what one should mean by a solution. Let's say, the most natural kind maybe is a classical solution. By classical solution, I mean the following, well, there's a free boundary. This is the boundary of the positivity set. And on every point, so the free boundary here is smooth. And on every, like locally near the free boundary, on one side you have the positive phase, on the other side you have the zero phase. And on the positive phase, well, gradient of u from the positive phase makes sense, and it should come in with slope 1. So that, okay, so this is at least a reasonable notion of solutions, a classical solution. I look at this problem, and this is the most natural thing that I can write down. So let's look at some examples of solutions. I'm going to show you a bunch of examples to see how we feel about classical solutions and other kinds of solutions and which ones we should really be using. Let's start with, so there's some trivial examples of solutions you can have, like a zero solution and so on. Let's look at the 1D solutions. Xavi already showed you the 1D solutions. Here I also have like a picture here. So this and this are, these three over here are classical 1D solutions, right? The 1D solution will have u being linear when it's positive, and if it touches the zero set, it has to do so at slope 1. So these are the only possibilities. Now, if you take a limit of this one, as the two things get closer together, you will get this wedge one that was very important to Xavi. This one is not a classical solution as per my definition, because it's not, this is free boundary point on which you're not zero to one side of it and positive to the other side. So here I have a limit of classical solutions, which is not a classical solution. So if you want to have, so essentially I want to construct solutions which are non-minimizing, and my only ideas in order to construct them involve taking limits of things. So I want the notion of solution I'm using to be stable under taking limits. That's sort of that's my requirement. So I'm happy with classical solutions in principle, but I do need to include limits of them. So in particular things like this, I need to expand my definition here. Okay. Now we can also look at radial examples in higher dimensions. It's not hard to compute here. You can look for the radial solutions are going to be like a fundamental solution outside of a ball. On the ball, it's 0. And you can compute like what is the multiple of the fundamental solution you have to use. If you do the computation, it's like this. This is not important, but so the r here is the size of the small ball where u is 0. The thing I want to point out is that as the ball gets smaller and smaller, notice there's this factor of r in front. Like this stuff is kind of of order 1. So there's a factor of r in front. So as the ball gets smaller and smaller, the solution gets flatter and flatter, and it goes to 0. So the limit of these solutions is the 0 solution. And the thing I want to emphasize about that is, okay, so the positivity set of this is the complement of a tiny ball. So it gets closer and closer to the entire space. The positivity set of the 0 solution is empty. So the limit of the positivity set is not the positivity set of the limit. So you have this kind of failure to converge here, which will be important later. Okay. Now, are there other solutions? Well, so here's some more entire solutions that are known. These are periodic solutions in 2D, and they look like you take a lot of holes. Like, so you take a line in 2D, And on this line, periodically, you arrange a lot of holes. I mean, they're like convex holes. They're not circles, but they're somehow, you can think of them as perturbations of circles. At infinity, it looks asymptotically linear on each side here. And you can compute a blowdown limit of them, and I think I write that here. The blowdown limit is like this. It's like some multiple of the coordinate, so that's the x2 coordinate here. They're periodic in like the x1 direction. So it's like a multiple of the absolute value solution that we had before, but it's not a multiple 1. This alpha is less than 1. It has to do with, well, the sizes of the holes sort of at scale 1. And in fact, there's one solution, which is 1 periodic and has a blowdown limit for each alpha between 0 and 1. So the alpha parametrizes this family of periodic solutions. And you can get any alpha between 0 and 1. So this is a blowdown limit. So it's a limit of classical solutions. These are classical solutions. Everything is like analytic for them. So if you want to incorporate limits of those solutions, you're forced to also consider this as a solution, which is a little bit weird. This looks like it doesn't even really solve your free boundary problem when you first look at it because the slope is not 1. But it is a limit of solutions. So this is something you're kind of forced to deal with. Okay. The other thing that you should be aware of when kind of working with this problem is there's a variational form. Xavier did show you this. Which is you can minimize the Dirichlet energy plus the volume of the positivity set, essentially. And so if you have a critical point of this formally, like if you have a classical thing which is a critical point for this, then it is a classical solution of Bernoulli. This is just a computation. I mean, and you can study minimizers of this and so on. So Alt-Caffarelli in a famous paper studied minimizers of this rigorously, and they developed a regularity theory for minimizers. And minimizers are really well understood here. This is a problem where a lot of work has been done on minimizers. They have a satisfactory regularity theory of the free boundary and so on. I want to go beyond minimizers because I want to construct solutions which are non-minimizing. So this is, I'm not satisfied with minimizers. Okay. So this is, as I said, I want to have solutions which solve the problem in some sense, right? Like I want them to be solutions in a recognizable way. I want them to include all classical solutions, and I want them to be closed under limits. And okay, so you can think of this in a different way, which is, well, what do limits of classical solutions look like? Can you characterize limits of classical solutions? And to help us do that, let me introduce some notation. So I'm going to call, so I'm going to subdivide the free boundary into 2 kinds of points, regular points and singular points. This is not a standard way of doing it. So by regular point, I mean points where the Lebesgue density of the positivity set is between 0 and 1. So this includes the thing that people usually call regular points, which is the reduced boundary. It also includes all Alt-Caffarelli, like minimizing cones, for example. But the things that this includes, which are not reduced boundary, have small measure. So this is not. Singular points are ones where the Lebesgue density of the positivity set is 1. And so that includes things like the absolute value solution that has a singular point in my definition. It potentially includes other kinds of things. I don't know a priori that this is how every Lebesgue density 1 point should look like. Okay. So what are the notions of solutions that are available? Like if you go to the literature and you try to find some. Well, so the most common one is minimizers, as I described. Minimizers is kind of a global property. So the 1D solutions may or may not be minimizing depending on exactly what the parameters are. But because of this, limits of minimizers are minimizers. And so minimizers are like a nice family that you can consider all at once. But I'm not happy with them for unrelated reasons, right? It's just too restrictive. Okay, so if we don't look at minimizers, you can look at sort of outer variation solutions, target variation solutions. Here, the idea is, well, I look at critical points for the energy with respect to just perturbing the U, right? So my energy is minimizing over U. Then I perturb I perturbed the function, and I want the derivative to be 0. This makes sense, and this is probably this is also a notion of solution that's been reasonably well studied. Sometimes it's called the weak solution. Like if you read Alt-Caffarelli, they talk about more or less this notion of solution. The deal with it is that, okay, so the absolute value of x in 1D is not an outer variation solution in this definition, because you can actually do a deformation, an outer deformation, which decreases the energy like linearly in T. But on the other hand, all of the other ones, any classical solution is an outer variation solution. So that immediately tells you these are not stable under limits. I can take a limit of these and I get something which is not one of them. These do have a reasonable regularity theory. This is something that Alt-Caffarelli already kind of noticed, but they don't have a good compactness result. I don't know that I can take limits of them. They don't have they have no singular points in my definition of singular point, which means there's no points of Lebesgue density 1, right? So they do have Alt-Caffarelli cone style singular points. So that's okay. Well, so if we're not happy with that, how about domain variation solutions? Like in some geometric problems, like harmonic maps, it's common to distinguish between doing domain variations and doing target variations, right? And so here I will instead only allow variations which are given by pushing forward the function under like a flow. And then it has to be a critical point with respect to those kinds of deformations. So I only deform the underlying space. When you do this, the variation that ruled out the absolute value guy is no longer available. So that thing actually is a domain variation solution. You'll notice I'm also making some additional assumptions, like the fact that it's Lipschitz and harmonic when positive, because unlike for the outer variation solutions, this doesn't follow immediately. In 1D, what this is saying is, okay, the things we like, so the regular solutions, right, the half space kind of solutions are domain variation solutions, so are any multiple of absolute value. So for a singular free boundary point in 1D, what it says is the slopes on the two sides have to match. That's what this notion is saying. And so, I mean, this seems kind of, if you were to just look at this abstractly, it would seem not good because it's including a lot of stuff which is not solving my free boundary problem. But I previously tried to convince you that actually we should be happy to see these because these are limits of classical solutions. And so this includes all the limits of all the examples I had before. So this is the notion I want to sell you on, that this is the correct notion to think about when you're talking about stationary solutions to Bernoulli. Okay, there's also, you can look in the literature and you will find a lot of stuff about viscosity solutions. Viscosity solutions I'm not going to, let me not define them, but it's based on having a maximal principle. There's a kind of comparison principle between two solutions which touch. And you can use this to define a notion of viscosity solutions. Viscosity solutions at regular points is like a very nice notion that has like a partial regularity theorem available and so on. So this is used oftentimes in the minimizer theory as well. But at singular points, my singular points, Lebesgue density 1 singular points, essentially you can only touch those singular points sort of from below. You cannot touch them from above by a smooth thing. So you only really have one viscosity inequality there that's meaningful. And so what it ends up saying is that locally, if in 1D, if I have a viscosity solution, then and I have a singular point, then both of the slopes have to be less than or equal to 1. They don't have to match, they just have to be both less than or equal to 1. And this is stable under limits. Viscosity solutions are stable under limits. And this is a nice notion when it comes to, for example, proving Lipschitz estimates and to pair with the notion of domain variation solutions I had before. But if you're trying to prove free boundary classification theorems or something like this, some kind of regularity results if you want, based on just this notion, this property on the free boundary just seems very weak. It only gives you some kind of inequalities, and it seems like you can have very, very poorly behaved free boundaries while still satisfying this. Okay, so fine. I'm trying to sell you on domain variation solutions, but I have to actually justify that they're a good notion. I mean, just because it works on the examples doesn't prove anything. So are they stable under limits? So let's try and decide this, right? Like we can write down the domain variation formula. If I have a vector, so I have a flow which is generated by the vector field xi here, then the domain variation formula looks like this. So this and this term you should maybe recognize. This is a domain. This is the variation of the Dirichlet energy on domain variations. This is what you get when you prove Pohozaev identities or like in harmonic maps. It's the same thing. This is the term that's specific to the volume part. And let's say I have a sequence of solutions in this sense, which are converging, let's say, strongly in W12. The way in which the solutions are converging to their limit is not so important here. Then this term passes to the limit, right? And this term also passes to the limit. Those are fine. But this term, I mean, this does not pass to its limit. I mean, I gave you a specific example, right, where the limit of the positivity set is not the positivity set of the limit. So that's exactly saying that this function does not converge pointwise to the limit here. So I cannot just stare at this formula and say, well, take a limit of all of the terms and then it works. So it's actually not clear from this that limits of domain variation solutions are like a reasonable class of functions. You can do some stuff here, and based on this, the sort of previous best result for limits of domain variation solutions looked like this. This is due to Georg from like 20 years ago. So in the limit is some kind of generalized domain variation solution, and it has a structure. So to interpret kind of what the PDE is for the solution, you can write down the Laplacian measure. So the functions here are subharmonic. Laplacian is going to be a positive measure, and you can try to figure out what the measure is. And so here, this part here is this Hausdorff measure restricted to the regular part of these are the regular points in my definition, like the ones with a big density between 0 and 1. This is what you expect if you have a classical solution. This would be the only term you have. This is just like a computation in 1D, essentially. Then here, sigma double star are the singular points where locally you look like an absolute value. This is the only kind of singular points I've showed you so far. So if you look, so what Georg proves in this paper, this is that this is actually a set with like, well, it's n-1 rectifiable. So the part of the measure supported on this is what you would expect if you actually had points like this. So it has a multiple 2 because you have the same slope from both sides. And then there's the remaining singular points. These are in particular I mean, these are points where the solution is like little o of r. So if you do a blow up there, so at these points you see an absolute value. If you do a blow up in the same scaling here, like the natural scaling for the problem, this is like a Lipschitz rescaling, you just see 0. And it's not clear how to count those points, and so there could be some remaining part of this Laplacian measure which is supported there. And there was no, I mean, there was no way of estimating the size there, so this made this theorem kind of hard to use because of this. Now, what we can now do better. So this is the main theorem I want to show you. Let me state it like this. So I have UK here, it's a sequence of domain variation solutions, and they're converging to a limit, let's say in strongly in W12. Then first, the limit is a domain variation solution. So previously I showed you the formula, right? And I said you cannot pass it to the limit. But if you think about the example I gave you, where I couldn't pass it to the limit, that was the radial solutions, right? They were, I had, the 0 set was like a tiny ball and it was going to 0, and then in the limit I get u equals 0. But u equals 0 is a classical solution. It's a domain variation solution. So in that case, it's, I cannot pass the formula of the limit, but the limit is still fine. Now I'm telling you that that's always the case. And the reason it's always the case is because I have a further thing here. Either the limit is identically zero. You should assume that the domain in which everything's set is connected here. It's actually true. So either the limit is identically zero, or the positivity set converges to the positivity set of the limit, and the free boundary converges to the free boundary of the limit. So this is the part that that Xavi commented on in his talk. So this is saying that this radial example where you get zero in the limit, getting zero in the limit, that's actually the only thing that can go wrong. That it just goes to zero everywhere. Otherwise, you have an uprating of the convergence here. You can also write down the Laplacian measure, and that part that was supported on the very singular points where you're little o of r, that's not actually there. That's zero. There's no part like that. And the full singular set, so like the points where you're locally like an absolute value, and maybe all the other points here, is n-1 rectifiable and has like locally finite. Well, like it has finite n-1 dimensional Hausdorff measure away from the fixed boundary. Okay, so this is our classification for, well, this is you can think of it as a compactness theorem or as like a regularity theorem if you want for state-term solutions to Bernoulli. Okay, I have one slide about like ideas from the proof. Let me maybe make some remarks about proving it. So you can think of this as an a priori estimate, if you like. It's a bit weird to think about it as an a priori estimate, but at least this last part where I'm saying that the n-1 dimensional Hausdorff measure is finite does make sense as just an a priori estimate for stationary solutions. And this is actually the part that you should try to prove first. These other parts kind of follow from this rectifiability, this, and maybe like slightly stronger things along the way. Yeah. That's right. So there's no, so the sequence which is so there's yes. Yes. So you just have a constant sequence of yeah. So in the original part, you also can't have it. So I mean, so in a classical, if I have a classical solution, let's say I have a sequence of classical solutions, then the only part that you would see is this. You would see this part if you have something which locally looks like an absolute value. I'm telling you that so for every domain variation solution, you have this classification for Laplacian. Right? So you never have this part supported on the singular set. So we don't prove that this like degenerate singular set is just not there, but we do prove that it's at most n-1 dimensional. And since the u is little o of r at every point there, that measure, I mean, like to actually have a positive measure there and have u be little o of r means this set had to be larger than like n-1 dimensional. And that's not the case. So that's why it's not there. Okay, so to prove it, you need sort of two ideas. One of the ideas is that, so the deal is, so indeed, so the part that you want to analyze is exactly the singular points, right? To get to here, well, to get this part, I need to prove that these degenerate singular points are not that many of them. And to prove this, I need to prove the same thing essentially, right? So that's what my focus is, just to try to count the number of these degenerate singular points where I blow up to zero in the Lipschitz topology. And so so there you can do blowups, but they're not helpful, right? Because you just see zero, and that doesn't give you any information. So the first idea you need is, so Georg had this other monotonicity formula. This is not the usual formula you use for this problem, the Weiss formula. This is a different formula. This is like a frequency formula. So this looks like Almgren frequency for a harmonic function, except my energy includes the term in the Bernoulli energy, and then I subtract 1. But this is not like a perturbation on Almgren's formula in the sense, so this is a formula which is exactly monotone, right? So if you differentiate it in R, because of the free boundary problem structure, like this is actually just monotone, and the derivative controls the quadratic remainder you usually see with a frequency type formula plus like some additional positive thing controlling something to do with the volume here. So this formula works at these degenerate singular points. I should say, this is monotone at any singular point. At any point where the Lebesgue density is 1 for the positivity set, this is going to be monotone. And at those points, this is actually giving information because, like Almgren's formula for harmonic functions, it's kind of capturing a finite order of vanishing, right? So this is like a kind of idea that should be familiar from like unique continuation. Now, when you see this and you realize this is monotone, you say, okay, fine. So let me do the same thing that people do when they prove, for example, nodal set estimates for harmonic functions. In fact, this theorem implies nodal set estimates for harmonic functions. What you can do here, if you like, is that, so if you take a harmonic function which is sign changing and it takes absolute value, this is a domain variation solution to Bernoulli in my definition. So, and the zero set for that, the free boundary is exactly the nodal set of the harmonic function. So this is like a nodal set estimate for a harmonic function in that case. So what do people do when they prove nodal set estimates? Well, you are supposed to write down your Almgren formula, you do blow-ups to see harmonic polynomials, you say something about the zero sets of the harmonic polynomials, and then you try to piece that together upstairs. So when you try to do blow-ups for the solutions to Bernoulli here, the issue is, well, you're doing blow-ups and not in the scaling which preserves the free boundary condition. The free boundary condition has a specific scaling under which is invariant. It's not invariant under other scalings, right? It's gradient equals 1 in the free boundary. So if I do something which is like much more degenerate than this Lipschitz scaling, then my free boundary condition blows up, if you will. So if I just do Almgren blow-ups, I mean, they converge weakly to their limit, but I don't know that there's a PDE for the limit. So it's really hard to understand what's going on with the blow-ups in this case. So that was actually, this is sort of, even if you have the formula, this is really not clear what to do here. So what we do instead is we do this Naber-Valtorta covering argument, and we use there that like, this is a part of the Naber-Valtorta argument, it's usually not so relevant, but what they do in here is they say, well, okay, you don't really need to be doing blowups at arbitrary points. I mean, why do you need to do blowups at arbitrary points, right? So I'm trying to prove the size of, something about the size of this set. I want to show that it's, it's n-1 dimensional. So let me only look at points where it's like really large, right? Where I have a lot of points kind of in general position. And if I have, so if it looks sort of n-1 dimensional locally, there are enough points so that it's spanning an n-1 dimensional object, then, well, I can do a compactness argument, kind of like a blow-up argument there. But because I have this Almgren formula and I can use it at each one of those points, it's like I have something which is in the limit is homogeneous with at each one of those points, right? So it's homogeneous with respect to points spanning an n-1 dimensional object. And the only way that's possible is that it's one-dimensional. So really, you only need to do blowups, or really like a compactness argument, in a configuration where you're approximately 1D. And that's much easier to understand. So that's a case where you can actually pass the PDE to the limit, sort of, and you can classify the limiting configurations. So we avoid, so by doing this, we avoid having to consider like arbitrary bad blowups and only need to do them at these more reasonable looking points. Okay, that's maybe all I want to say about the proof here. Yeah. So let me instead give you a small application to constructing solutions. So this is this gravity water wave problem. So the idea is, maybe let me draw a picture of the configuration here. So these are finite depth gravity water waves in 2D. So and they're periodic. So this variable here I call y. This one is x. We're one periodic in x, and this here is y equals 0. And the idea is, okay, so we have a fluid. This is like water. Up there, it's air, and we're trying to construct something which looks like a wave. And down here, you're solving Euler equation. This is incompressible Euler equation. And I'm looking for traveling wave solutions. So immediately I'm going to go away from this like transport type equation into a stationary equation. And I'm going to look for irrotational solutions. So that means the vorticity is 0. And that means you can solve for a stream function. The stream function will be harmonic due to this condition. And you can compute, well, what the stream function is doing on this free boundary here and on the fixed boundary here. So there are two boundary conditions in this water waves problem. One of them is just a, well, this is a traveling wave, right? So there's a condition that just says that the motion of the fluid, like essentially this top boundary has to be contained inside of a streamline for the fluid, right? So this is just, if I take this configuration and evolve, the fluid is not moving kind of normal to my boundary. And there's a second condition which says that, well, the pressure of the air is constant and then has to match with the pressure on this side here. And if I do that, then I get, well, I get two conditions on the top here. One of them is that the stream function is constant. This is coming from this kinematic condition. And the other one says that gradient u squared plus y. The y is from the gravitational potential. I should have included it here. But so the y is due to gravity pushing you down. This quantity should be constant, and this is from that pressure balance condition. This is called the Bernoulli law. The Bernoulli law is like this empirical phenomenon that the pressure here is constant and the pressures match. And this is why this is called the Bernoulli free boundary problem. I mean, from this application in particular. Okay. So when you get rid of the fluid variables and you change to the stream function picture and you kind of rescale things, what you see is this. So you're going to have, so the u here is the stream function, and so the u will be 0. I've normalized so that it's 0 here. U is going to be 1 along the bottom. The bottom should also be in a streamline for the same reason, essentially. Then here I have an additional boundary condition, gradient u squared. It's not constant. It's a minus by, again, due to the gravitational potential. So it's a minus by. A and b are constants which have to do with the physical parameters there, like the pressure and the gravitational constant. Well, yeah, and there's a PD here that's harmonic here. So I'm looking for a solution to this free boundary problem, right? And it should be periodic in this variable. That's the one. Okay, so if I'm trying to find a solution, how do I do it? Well, maybe I should just minimize the Alt-Caffarelli energy, right? That seems like a reasonable approach here. And in fact, you can try doing that. Maybe I should say, so this is not how the water waves people try solving this problem generally. Water waves people are actually very, very good at solving this problem, but they do it completely differently. They have an approach based on, well, so you can take this picture and you can change variables so that the top becomes flat. And when you do this correctly, you get an integral equation in 1D. And you can study this integral equation and do bifurcation theory. And with global bifurcation arguments, you can produce many solutions to this. This has been studied a lot. There's a really large literature on this that I'm not close to summarizing here, but these are some older works where they sort of pioneered this approach. Okay, we want to do something different. Can I do a direct variational argument based on the fact that this is a free boundary problem and I like the Alt-Caffarelli energy? And indeed, you can write down an Alt-Caffarelli energy here. It's very similar. You have this weight here, but this is fine. And you can minimize this. And critical points of this formally correspond to solutions exactly of this problem. Okay, so in fact, Leone and collaborators studied this approach and whether or not you can minimize it, But the problem with minimizing it is that actually you get a really boring solution. You can minimize it and you get a solution which is constant. It has a constant free boundary like this. So you get a flat wave. And this is physically, it makes sense. That is a solution to the periodic water wave problem. But I want different ones, right? I want ones which are not this one. So how do we do it? So I can classify all of the all of the 1D solutions here. Okay, I can classify all the 1D solutions. This is not very hard. And depending on the choices of parameters, A and B, so that for the parameter range that I care about, there will be 3 of them. There's one over here, which I call U minus. There's another one, which I call U plus. And there's one more solution, which I call U infinity, which is identically 1. So what this means is it's all water. There's no air. This is you can think of it as kind of a limiting configuration, if you like. This is the fact that you can discard it as a meaningful physical solution, but it exists in this energy formulation. And then there are these 2 which are actual like physical solutions. This is not hard to do. So then the deal is that U minus is a local minimizer. U infinity is a local minimizer. U plus is not a minimizer. U plus, even in 1D, so in 1D it's unstable. So I have 2 minimizers. And whenever I have 2 minimizers, I can try to construct a solution in between by doing like min-max, by doing mountain pass theorem, right? I have two wells in my energy. And so I can look for like this critical point between them by doing mountain pass theorem. And formally, okay, this should always work. I should always get something. So let's do it. The problem is, okay, maybe I construct it and it's just going to be this one, U plus, the 3rd solution, which I said is unstable. That would also make sense, right, in this picture. But you can do a further computation. And the computation you can do is that, well, whenever you construct this mountain pass solution between 2 minimizers, it formally has Morse index 1. It's unstable, but there's only one unstable direction. On the other hand, this is a completely explicit solution for which I can compute the Morse index by hand. And depending, again, on the parameter range here, I don't show the thing you have to assume about the parameters because it's a little bit complicated and not enlightening, but for a large number of the parameters A and B, actually it's unstable, but it actually has Morse index 2 or more. So because it has such large Morse index, it cannot be the thing you constructed by doing mountain pass theorem. You had to construct something different. But these are the only 1D solutions, so whatever you constructed by mountain pass theorem had to be not 1D, right? So there we go, right? We've proved that we constructed a water wave. So as a formal argument, this seems very reasonable. The problem with this is that how do you actually apply a mountain pass theorem to this context, right? So this is an energy which is like, I mean, it's not even differentiable. And mountain pass theorem usually requires you to check Pelley-Smale condition or something like this, which is something that requires some amount of regularity for your functional. Indeed, for many kind of nonlinear problems, I guess most famously minimal surfaces, doing min-max constructions or doing mountain pass is really not trivial for this reason, right? So unlike for just semi-linear equations, doing min-max for minimal surfaces requires a whole like this Allmern-Pitts theory, or it's much more complicated than just applying an abstract mountain mass theorem. So here we give kind of an approach to doing this for Bernoulli, which uses the compactness theorem I showed you earlier and doesn't require anything else. So the idea is very simple. You take your energy and you regularize the characteristic function in here, right? So I take this and I like mollify it. This is a very standard idea of in free boundaries. This is like looking at the singular perturbation limit of a semi-linear equation. This is like what Nicholas had in his talk yesterday for the segregation problems. But you can do this for just for Bernoulli problem. And the energies converge in some sense, right? So there's like gamma converge. And so the energy landscape for the regularized problem is basically the same. You still have kind of two energy wells, and you can still look for the thing between them. And for the regularized energy, you can do mountain pass theorem, like the classic mountain pass theorem you'll find in a book. And so you find a critical point for each epsilon. And then you just take the limit in epsilon, okay? You just take the limit in epsilon. These u epsilons, I mean, they solve the semi-linear equation. And our compactness theorem for domain variation solutions works for the semi-linear approximation just fine. So you can take our theorem is relying on some kind of regularity properties of the limit, not anything about the sequence per se. So the theorem we prove will say that the limit of these u epsilons will be a domain variation critical point of this this energy. You can also pass the Morse index to the limit, sort of. This is a bit different from minimal surfaces where you can't just do that for free. But when you compute the second variation for Bernoulli, under the kind of upgraded convergence that I mentioned, the second variation just passes to the limit. So you can do that, and you also get that the Morse index of the limit is less than or equal to 1. And then that's enough, right? That's enough to tell you that the limit is not 1D because it's not one of these three guys. Now you're done. You have a solution. You can now spend the rest of your life doing regularity theory on it. So this is a paper now which is available on arXiv, and we do some additional regularity theory. We can prove more than just what the compactness theorem would tell you. Here, I mean, so we cheat a little bit. So here we can use the special structure of this problem to get more regularity. So one thing you can do here is you can symmetrize. There's a symmetrization you can do, which tells you that the solution is monotone in this direction once you symmetrize. This works for the mountain pass theorem, and so you can take limits of those, and those will be more regular. Okay, so let me maybe not comment more on the regularity theory. Here, in principle, you should be able to do more because, of course, this is like a finite Morse index solution. So this is actually a bit more like the theory that Xavi was talking about. This is in dimension 2 as well, where it's even easier. So based on that, you expect to have better regularity properties than just for arbitrary stationary solutions. But I guess my point here is you can do this argument just kind of blindly, right? You just use our compactness theorem, and you didn't really need to worry about anything else. And so hopefully this is a useful approach to constructing solutions to these kinds of problems in general. Okay, thank you.